Yes, Assalamualaikum warahmatullahi wabarakatuh, and good morning. So we will continue our class. So can you guys hear me?
Yes, doctor.
Okay, good. Okay, all right. So today we're going to have, as usual, so we have 2 hours for Tuesday class, and the first part we're going to finish this topic, which is the LTI system, and then on our second part later, we will start a new chapter, which is Z transform. Okay, so let's do this first. Okay. LTI system, let's see. So where we stopped last time. So we're done with convolution. Today it's supposed to be properties of LTI system. Okay, just before that, so let's do some recap. Okay, so what we have learned so far. Okay, so what is this course? This course is about digital signal processing. So we are actually processing a discrete time signal. Okay, so that's why in first week, so already introduced on what is a discrete time signal. Okay, so because most of the signal is actually originally, it is continuous. Okay, like audio, maybe voice, temperature, EEG. So any physical signal is originally continuous, but we need to process this signal using a digital system. Okay, so that's why we need to convert this continuous signal into a digital signal, so which we call a discrete time signal. Okay, and we have seen that. So example, we have xn, and this is just what is a discrete time signal. It is just a sequence of values. After you do sampling, what you get is a sequence of values. So maybe you can have, let's say, 2, 3, 4.5, and then suddenly 0.2, and etc. Okay, and the one that we need to also see from this sequence is the index. So we start with index 0, 1, 2, 3, etc. Okay, so that is actually discrete time signal. So this is the first week. So we have learned that on first week. And then we go to, so this is number 1. So number 2, so we have seen what is a discrete time system. Okay, so discrete time system. So generally we have seen what is a discrete time system. So it is, what is this? So what we need is, so we should have input signal, and then the output signal, and then at the middle is the process. Okay, so when you have those three things, input signal, output signal, process, so that is what we call a system. And because our input and output is actually a discrete time signal, so this is a discrete time signal, so this is a discrete time signal, then we call this a discrete time system. Right, and this is a process. So we have seen this process. So we have arithmetic operation. So arithmetic operation is those mathematical operation like a plus, minus, multiply, divide, power, can be sine or cosine. What else? Log, right? Those are mathematical operation. So we have seen that. So that is one of the process. So arithmetic operation. And then another one is operation on index. So what we have covered is like a delay. So what is delay? Delay is something like if you have n, maybe plus minus of nd. So that one is a delay. And then we have folding. So we have folding, so which is minus n. And then we have actually another one, so which is what we call selection. So this is the operation like you have 2n, and maybe okay, let's put that. Don't put a number, put some variable. Alpha n, so let's say alpha is 2, so 2n. So you will pick samples every even of n. Okay, so that one if the alpha is 2, and we can have also alpha n squared. Okay, or generally we can put it as an alpha n to the power of something. Okay, so that one is a selection. So it means that if you have alpha n or n squared, so you're not going to, what is the process? The outputs, this yn. So you're not going to involve every samples in the inputs. So if this alpha is 2, so you're going to process only the even index. Okay, so if let's say we have n to the power of something, so then you will pick up, let's say this is n squared. So what you're going to select only a certain sample. So which is if this is a 0, n is a 0, so 0 to the power of something is still 0. If it is a 1, and then you're going to pick still 1. If this is a 2, so if this is a 2 to the power of 2, then you jump to index 4. So you will jump based on this operation. Okay, so that's why we call it a selection. Folding is just you change sign of the index. Delay going to plus or minus on something, some values, nd. So this is what we have generally of a discrete time system. Okay, so we have input, output, and then a process. And then what we have seen is the properties. So this is very important. So we have 4 properties that we have covered. So which is number 1, linearity. Number 2, time invariant. Number 3, stability. Number 4, causality. Okay, so we have covered that. So if we have a discrete time system, so we can check its properties. Okay, so we are looking at the process. So for linearity, so we are checking this one. So we are checking this arithmetic operation. So if it is linear, actually this is it needs fulfill linear system should fulfill what we call a superposition theorem. Okay, but if it is a linear, we have conclude, so it can only consist only what we call a weight multiplication and the other one is summation. Okay, so we should only have these two operation. And then the time invariant, so if the system is time invariant, so we should only have a delay. Okay, so only consists delay. So this one, so not this one, not this one. So then we will have a time invariant system. So other than that, the system will be time invariant or not time invariant, and the system will be not linear. And then we have checked also stability. What is the stability? We are checking on bounded input, bounded output. Causality, no future of input or output. Okay. So these are what we have covered so far. And then, so actually that one is in week 2. So then we go for very specific, this one. So when it is a linear and when it is a time invariant, so this becomes a very special system. So we call it LTI system. Right, and when you have LTI system, so do I have more space here? So when you have an LTI system, so it becomes a unique and special system, because originally at the center, this is a center. So what you have is a process. Okay, you will have a process. So, but because it is a LTI system, so because the operation is just a weight multiplication, summation, and then just a delay. So this process, we can represent our system to have Hn. What is the Hn? Hn is the impulse response. If it is just a general system, so you won't have that Hn. For LTI system, you will have the Hn, the impulse response inside. And so what we would do here is actually, what is the Yn? Is simply as, so we have covered this, Xn, we do convolution, the star to Hn. Okay, so when we have a convolution, so what is this? What does this mean? If you have a convolution, means this is LTI system. Only LTI system can do the convolution. Okay, if it is not linear, not time invariant, so this is just a process. You need to solve the equation. Okay, for example, what is the example of this one? So Yn equals to, let's say, Xn square. Okay, there is no convolution here. It's not possible to have a convolution here. So you need to solve this equation. Whenever you have a system, so how to get, let's say, a y of 10, so you need to compute from this equation. Okay, so example, you want to have a y10, so you need to have a x of 10 squared. So you need to check x10, what is the value, and then square it. Okay, but this one, you have options. Let's say we have example, Yn equals to Xn plus 2Xn minus 1. Okay, so what is this? So this is what we call a difference equation. So again, because this is a special system, this is the special LTI system, even this equation, so we have a name for it. It is what we call a difference equation. This one, there is no name. So it's just an equation representing a system. And this is not linear. This is time invariant, but it's not linear. Okay, so this equation is just representing a discrete time system. There's no name for it. But for LTI system, so there is a name for it. So we call it difference equation. When the system is an LTI system, that equation, we call it difference equation. Right? So it means that automatically, if let's say you are given, let's say you already know that you are given difference equation, automatically you know that that one is actually LTI system. Okay, so, and so what we have seen this one, because from this, so what we can do is we can convert between a difference equation and Hn, impulse response. So we have seen that for one system, which is the FIR. So because we have two types of impulse response. One is the FIR, finite impulse response. Another one is the infinite impulse response. So we have seen how to convert Hn to difference equation for FIR system. Okay, so what is it? So Hn of this difference equation is just actually the weight of that equation. What is the weight? The weight is this is 1, and then this is 2. So our Hn here is simple as 1, 2. Okay, so we have done that. So straightforward for FIR system. So So this is where we have two options on how to get yn. So you can get yn by solving this equation. Find xn and then plus 2 xn, xn minus 1. Okay, so if you want to find a y10, so let's say you want to find a y10, so you should find a x10 plus 2x9. Okay, do that. Get your xn and then check what is x10, means that the value of input signal at index 10. And then this is the value of x, your input signal at index 9. Multiply by 2 and then plus with x10. Okay, then you will get your y10, means that the output signal at index 10. So yes, that is actually one option. The other option is because we already know that, because this is an LTI system. So the relationship is actually a convolution. So that process is actually convolution. So this is where we can also do a convolution. This one, not solving this one, but solving this one. Knowing what is the xn, now you know what is the hn. What is the hn? 1, 2. So that one is the hn. Then do convolution. So you have two options. Okay. So that one is for LTI system. If it is non-LTI system, so you won't have the hn, then you cannot do the convolution process. So you need to solve this equation, the relationship between the input and output. All right. Okay, so what else? So we have covered a convolution. I think those are that is so far what we have covered. Okay, so today we're going to look at the properties of the LTI system. So we have seen properties for generally for this discrete time system. So we are looking at linearity, time invariance, stability, causality. Okay, so because this is an LTI system, we doesn't have to look at linearity and time invariant anymore, because it's already linear and time invariant. So this is where we need to check the stability and causality. Right, so okay, so let's see. So this is for stability. In previous chapter, stability of discrete time system is achieved when Bibo condition applied. Right, so we can still use that. Because LTI system can be represented with impulse response, because this is new for a general discrete time system. So maybe we do not know whether it has an impulse response or not. But if we know it is an LTI system, which is the linear and time invariant, so it has impulse response. Okay, so when it has impulse response, so we have another option to check for stability. So we can do this. We can check on Bibo, bounded input, bounded output. So now we have a new option. So which is we're going to check on our impulse response. Right? Instead of Bibo, stability of an LTI system can also be described with its impulse response. Below is the rule where the input signal xn is assumed to be bounded. Okay, because this is the rules, bounded input, bounded output. So input signal must be bounded first, and if the input signal is bounded, then we can check impulse response. So this one, what is the equation? The equation is just you do summation to the whole sample of the impulse response. Then check whether it is infinity or not. So if it is not infinity, then the system is stable. So from our previous example, so we have a hn equals to 1, 2. Okay, so this is actually obviously stable, because if we put it into this equation, the summation of hn, so you need to have the absolute value. And this is index 0, this is index 1. So n start from 0 up to 1. So what is it? So this is actually just h0 plus h1. So which is equals to 1 plus 2 equals to 3. And 3 is not infinity. Okay? Very simple to check. And actually, this is easier to check rather than checking the bounded input, bounded outputs. Because bounded input and bounded output, so you need to be very intuitive. Means that you need to really understand the system. Okay, you need to really know what is the possibility of input signal, and then what is the possible of output signal. Then after you know what is the possible output signal, it's not, it is bounded, the input signal is bounded, then we can say that it is BIBO. Okay, but checking on impulse response is quite straightforward. So you just do sum everything, every value that you have on your HN. So if it is not infinity, then the system is stable, right? So what we do here, so we are actually checking the properties of our LTI system on stability. Because we already know that it is a linear, it is a time invariant. So we need to check another two, which is stability and causality. And checking the stability, so we're not looking at BIBO, we can do that, but we already covered that. So what we do here is we check on impulse response. Because impulse response is unique to LTI system. And then let's look on causality. So causality for LTI system, the difference equation without past and future output. This one. So Yn, this one. Okay, I'm going to skip this one because I'm going to make this as simple as possible. For a causal system, no future inputs are involved. So we already know that. Okay, we already know that. So thus the range of K, this one, if you look at that one, that K should start with 0. And what is the conclusion? The conclusion is when we are looking at our impulse response. So what is this? So this is the impulse response. Again, we are checking on our impulse response. Why we are checking on impulse response? Because LTI system has an impulse response. Okay. So can we check on the difference equation? Yes, we can do that also. So we already know that by looking at the difference equation, we suppose not to have the future input or outputs. So that is actually causal system. But now we are looking at the impulse response. So looking at the impulse response, what is the rules? Hn should be 0 for n less than 0. Okay. From previous example, so we have a 1, 2, and this is index 0, this is index 1. And if you plot that, so this is actually 1. Okay, so what is this? What is the x-axis? So this is n. And if you are looking at -1, -2, this is 2. Okay, so no value, or the value is 0. Okay, so this value is 0. So Hn is equal to 0 for n less than 0. For n less than 0, which is -1, -2, and so on. So we can see that the value are 0. So we can conclude that this system, this Hn, this impulse response, is causal. Okay, as simple as that. So any questions so far? So we have seen stability and causality. So this is a second method on how to check causality and stability. Still very easy, right? Okay, the third one. So this is additional properties. We don't really look at this when we are covering the general discrete time system. Okay, we're just looking at stability and causality. So, but we are looking at another properties here. So we call it impulse. So we have some rules here. If a signal or a system, okay, so when it is xn, okay, now everyone needs to be very careful, okay, because normally when it is xn, so this is input signal. Unless otherwise stated that xn is not input signal. Okay, so if it's not stated, xn supposed to be the input signal. Hn is what we call an impulse response. So what is the similarity of these two? So, and we can also have a yn. We put this as an output signal. And these three are actually in maths. So it is actually in a form of a vector. What is a vector? Vector is a sequence of value. So yn is a sequence of value. Xn is a sequence of values with its index. Even Hn is actually a sequence of values. This example, this is Hn. So what is the what are the values? So we have a sequence of the first value 1, the second value is 2. With index, the first value, the index is 0. The second value, the index is 1. Okay, so and we can have also xn, same thing, looks very similar. Let's say we have 2, 3, 0.5, 5. Okay, so let's say okay up to that one. So this is a 0, 1, 2, 3. So both are actually a vector, a sequence of values. Okay, that one is actually vector. So it looks the same, but it represents totally different thing. Yn and xn is a signal. Okay, but the impulse response, what does it represent? This is system. Okay, totally a different thing. First week, we learn about signal. Second week, we learn about system. Now, our signal and system looks the same. Okay, that's why do not confuse. So even though the how does it looks similar, so it represents a different thing. So if it is an impulse response, it representing a system. If it is a xn or yn, so this is if it is stated that this is output and input signal, so this is a signal, right? Not a system. So everybody needs to be very, very clear. So what is the difference between signal and system? Okay, any question on these two? What is the difference between a signal and system? So any part that's maybe might be confused, something? Anyone? We need to be very clear on this. Looks similar, but representing totally a different thing. Okay, so for impulse properties, so we have this. This is impulse, right? So we have seen two basic signal. One is impulse, we call it impulse, and representing it with the notation is a delta. So the one is delta n, impulse. Another one is actually a step, which is a un, right? Delta n, so this is what we call impulse. Un, this is step. And we call that impulse signal. Step signal. Okay? We don't call it impulse system. We don't call it a step system. So that is a signal. Okay, so that's why we call it a basic signal. So we have learned that one. So two basic signal. So if we have impulse signal, do convolution. Again, this is not multiply. So this is convolution. You do convolution to any signal, you will get that signal. Okay, you will cancel out the delta n. And if you do convolution with a delayed impulse response, a delayed impulse, not impulse response, this is impulse signal. Hn, impulse response. So be careful on the names, right? On the notation. So if you have a delayed impulse signal and then do convolution with a signal, so you will have a delayed signal of that input signal. Okay, so this is a minus nd, then your x will be delayed by nd. Okay, so because this is there is no delay here, so that's why it doesn't have any delay here. All right, so this is quite straightforward. So we just later we're going to use these properties, right? We're going to use these properties. And this is additional properties. Actually, this is additional properties so that we understand better what is what we call the linear and time invariant. And commutative, associative, distributive. Actually, this is not new. This is actually properties for a linear system. Okay, like when you do multiplication, just a normal multiplication or maybe a normal addition. So actually, those things are linear. So if you have a square, something to the power of something, that one is not linear operation. Okay, so that's why this is quite easy, because a convolution. This is convolution, so it has those properties of a linear arithmetic operation, like multiply. So such this, let's say you have a yn, you have a xn, do convolution with hn, so it is actually equals to hn convolve with xn. It doesn't matter you put a xn in front or hn in front, it is the same, right? So this is like if it is a multiplication, so a multiplied to b is equals to b multiplied to a. Okay. Associative is again the same thing. It's like a multiply and a summation. So if you have a xn and then you do the convolution with h1n and then do convolution with h2n. So actually you can do either one first. You want to do convolution between xn and h1n first, or you do this h1n convolve with h2n first and then solve the rest. So it is equal. It is the same thing, associative. Similar like multiplication, right? A times B times C actually equals to, if you want to do A times B times C. Either you want to solve this one first and then multiply by C, or you solve this one first and then multiply to A. So it is the same. It is the same. All right, and then this is distributive. Distributive is we have a plus here, similar to a multiplication also. So convolution, actually, because what is a convolution? Convolution is a process for LTI system. And what are the operation that you can have on the LTI system? It is actually weight multiplication, multiply, and summation, and plus the delay. Okay, so that's why it is following what the multiplication, the normal multiplication do, right? So it has all these three. So let's look at example, commutative. So this is a commutative. When you have a, let's say, example, xn, so we have 3, 1, 5. So we have 3 samples only. And this is hn equals to delta n minus delta n minus 1. Okay. So this hn is actually written based on impulse signal. And you should know that this is actually, if you sketch, delta n is, so this is delta n. But what we have is delta n minus delta n minus 1. So if you have this delta n and then you delete by one sample and then multiply by minus 1, so you should have another one here. So this is actually minus delta n minus 1. Okay, those two things. And actually this is just equals to 1 minus 1. Right? So we have two values, 1 minus 1. This one, this is 1, this is minus 1. Okay, so now, okay, we have that. So if we do convolution in front, so we put a xn first, and then let's do when we put a hn in front. So this one is where we put a xn first. So this is the n, so you put it there, the index 0, 1, 2, 3, okay, in sequence, and then xn. So xn start at index 0. So put it there, 3, 1, and then 5. And then the hn, we already know that hn is a 1 minus 1, and then do the multiplication. So this is a 3, 1, 5, and then minus 3 minus 1 minus 5, and then do the summation. So 3 minus 2, 4, 5, minus 5. So this is when you do xn in front. And this one, when you do the hn in front. Okay, so we put a hn first here, and then 1 minus 1, 3, 1, 5. Now you need to multiply 3 times, because this is the first one. So 1 multiplied by 3, 3, minus 1 multiplied by 3, minus 3. And then do that again, you get 1 minus 1. This is 5 minus 5. Do the summation, you should get same value. This yn and this yn should equals. Okay, so it doesn't matter. So which one you do first. And this is associative. So for example, we have 2 things. So this is where when a system, so actually this is what we call a cascade system. So you have actually 2 systems. So one is a H1N, so there's an impulse response here. So what is impulse response? Impulse response is representing one system. And then we have a H2N. So actually this is another system. This is another system. When we do this, so actually what we call it, we are cascading the system. So we are cascading the system. And what is the operation between these? So when you have a xn and then arrow coming into this box, a system, so the operation is convolution, because this is LTI system. And whatever you have here, and then you have arrow coming into this second system. So this is another convolution. And this is the output. Okay, so actually we can write it as a yn equals to xn convolve with h1n convolve with h2n. You have 2 systems cascaded, right? So this is what we call a cascaded. And then of course you can solve this 2h first, the 2 impulse response. You can do the convolution first and then convolve with input. Or you can actually solve the convolution between xn and h1n first, and then do convolution with h2n. Or you can do the convolution xn to h2n. So this one, between this one and this one first, and then solve a convolution with h1n. Right? That doesn't matter. Okay, so this is let's say we have xn 111, h1n 2 minus 2, and then h2n equals to delta n minus 1. Again, this is written based on impulse signal. So what is this? So when h2n equals to delta n minus 1, if you plot that, so this is 0 because we have a delay of 1. So it's supposed to be here, and the value is 1. Okay, so that is actually delta n minus 1. Okay, so and how to write that in a vector? So in vector, so we will have h2n equals to, this is index 0, this is index 1. Index 1 is 1. So what is index 0? 0. So you should have a 0, 1. Okay, for this one, h2n is actually equals to 0, 1. So you can do that. You can do this. This is not a full solution. This is quite. This is actually a simplified solution. So you can do that. A complete solution for it. But whatever you do, either one, so you should get this result. So you should get this result. Okay. So please try it. So hopefully you will get everything similar. You should get everything similar. Okay. Either one. And this is the last one. So we are looking at another example on the distributive. So when we do a distributive, normally a system which have a distributive system, so there's a sum here. Okay, this is a sum symbol. So we have 2 system here. So it doesn't, it's not always a 2 system. It can be a 3 system. It can be more than that. It can be 5 system. It can be maybe up to 10 system. Okay. So, but distributive means normally we should have this as sum. So what does this mean? So how do we write this system? So it is actually xn, that one xn, a row means convolution, right? So xn convolve with h1n, and then this one, another arrow going to the second system, h2n. So this is actually xn convolve with h2n. And then those two will be sum. So that's why we have sum here. Okay, and also we can write it as the xn convolve with h1n plus h2n. Okay, because this is an arrow, so what we can do is actually we can group that into, let's say, a single system. So then we have arrow here, a single arrow. Okay, then you solve this first, and then do convolution. This hn do convolution with xn. And if you do that, you should get, let's say we have this example 1, 1, 1, the same thing, 2 minus 2, and h2n equals to delta n minus 1, the same signal, the same system, okay? The same xn, the same system. So we have two systems here. So one signal. So in this case, in this system, so what you'll get is at output yn, this is yn, so this is actually yn, so you get a 2, 1, 1 minus 1. Which one that you do, which one that you solve, so you should get the same output. Okay. What's next? This is just a summary of our LTI system. So later I'm not going to explain this one because it involves system function, frequency domain. This is later. So what we have now is just a difference equation and impulse response. Okay, any question? Am I too fast?
Doctor, can you go back to the previous slide?
This one?
No, just now.
Another one?
Yang tadi, the distributive.
Distributive, okay. Right, this one.
For the first equation, how did you get 2, -1?
This one. So
yeah.
Okay. So this is okay. Let's do this. Okay. So this is h1, h2, right? So actually we are solving this one first. We are solving the hn, which is equals to h1n plus h2n. Okay. So then what is the h1n? So h1n is this one, 2 minus 2. 2 minus 2 plus what is the h2n? So what is this? So we already know this. So this is actually 0, 1. So this is actually 0, 1.
Simple addition.
Okay. So what is a addition, multiplication, minus, divide? So we have seen that. So we need to do that on the same index. So,
okay.
Right. So 2 plus 0 is 2, minus 2 plus 1 is minus 1. Okay, so you get this one.
Okay.
Right.
Thank you, Doctor.
All right. Other question? Any other question? So this is very important because test 1 will cover this kind of thing, right? So test 1. So test 1, as you already know, so we already postponed it to 25th of November. It's supposed to be next week, but there's a few problems, so we need to postpone it to 25th. Okay, so it will cover up to week 4, which is this week. So whatever we cover this week, so it will be in the test 1. Okay, so let's see what will have, because okay, it's just maybe a few minutes. So let's see what we have so far. Okay, so what we are dealing with now is we're going to go through a LTI system. Okay, so actually from week 3 last week until the end of week 14 later, So actually we are only dealing with the LTI system. Okay, but of course in test 1, so you will be, there will be a question on a non-LTI system because we covered that in week 2, right? But what we will do is actually everything on the LTI system. So we have covered this, the continuous signal. So we do a sampling. So what is a sampling? Sampling, you should do this. There is a T equals to N over Fs or T equals to NTS. Okay, so you should know this. And then this one later. But now we should know that the Fs are supposed to be greater than or equals to 2Fn. So this is a Nyquist theorem, right? So we need to fulfill that, so that we can have a discrete input signal, which is, we call it Xn. And we have input, we have output. So this is a LTI system. And what is this? So this is a filtering. So what we'll cover is actually most of the time, until the last time, even in the designing part. So we are actually doing filter. So we're going to analyze filter. We're going to design a filter. Okay. But it doesn't mean that filter is, there's a lot of application on filtering. Okay, so actually my expertise is in image processing. So a good example on filtering that I can see here is, so when you do your camera, when you try to capture, let's say, a group photo, right? So it can detect faces. So do you have those camera? Even actually your phone can detect faces. Okay, so how does that algorithm detect the faces? So actually it is based on filtering. It do a lot of convolution, then it gets the faces. Okay, so that's why actually image processing is the basic is actually signal processing, because the image is just a 2-dimensional signal. So we're not going to cover this 2-dimensional signal in this course. But whatever it is, 1-dimensional signal, 2-dimensional signal, the basic operation, if we have an LTI system, so it is convolution. So now you know that you have your camera, you are capturing the image of a group photo or maybe a selfie. So actually the box that you see is actually the results of a convolution. So there's a lot of convolution happening inside. Okay, so we will learn about convolution the rest of this thing. And to do that, we should have, if you have an input, output, so you should have the filter itself. So you should have this filter. And that filter is actually what we call impulse response. This is the one that we have seen. So we doesn't call it filter yet, but we call it impulse response. Okay, we call it impulse response. So actually that impulse response is the filter. Okay, and what we have done is when we do a filtering, so either you solve a convolution or you solve the difference equation. Okay, because the LTI system, we can represent it in, based on two things. One is a difference equation, another one is a impulse response. Using impulse response, you do convolution. If you don't do convolution, you solve using difference equation. And we need to do some analysis to our filter. So this is the filter. Okay, see, this is the analysis. The arrow is actually connected to the filter. It's not connected to the input or output. So far we have done this. This is what we call a time domain analysis, checking on stability and causality. Right? So what does this mean? A stability and causality test is actually done on a system, so which is on the impulse response or difference equation. So it is not done on input or output signal, because it's not a properties for input or output signal. Causality and stability is a properties for system. Okay, so we have seen that stability, we can do BIBO, checking the difference equation. And we have seen this is on impulse response. You are checking that stability, you do the summation on all values of the impulse response. It should get less than infinity to make sure that the system is stable. Causality is very easy. When you are checking on the difference equation, just check whether there is a future input or output or not. If there's no future input or output, so it is causal. On impulse response, so you can check HN. It's supposed to be 0, for n less than 0. Okay, so these are so far what we have covered. And actually, we already have a system. So we already know how to get outputs. So we just do convolution. So what are the rest that we will cover? So next will be this one, after this next session. So we will cover Z transform. And then we do inverse Z transform. Later, there is a Fourier transform. So there is a Fourier transform here. And then another Z transform. Okay, and then design. So we're going to make some design. So there's a two part of design here. And in this slide also, you can see also the MATLAB function. So this is actually very useful for you to do the assignment, right? And if we look at the classification here, so what we have covered is actually on how to do the filtering in time domain. This one. So this is just the part that we have covered. And we have covered a bit on how to do an analysis. So this one is actually analysis. So we need to analyze our filter, analyze our impulse response. So what we have done is the analysis on time domain. So we will do analysis on Z plane. We will do analysis on frequency domain later. And this part, this is the later part. So maybe week 12, 13 later on how to design this filter. For now, the filter, which is the impulse response, is given to you. It's already there. But week 12, 13, 14, so you will design it. You will design it, right? So far, it will be given, and we need to analyze it so that we will understand the system itself, okay? But how to filter, you already know it. So how to do it? Do convolution, that's all. Or difference equation. Okay, so that I think that's all for this first session. So we will take a break. We will take a break for 10 minutes. So we'll come back at 12:10. Okay, so we'll go for a new chapter. Okay, someone is writing something here. I will read this. I would like to add also new modern high-end cameras uses two different processors nowadays. They can track the subject eye movement in live and refresh every up to 1/500 of a second. Yes, that's correct. Okay, that's correct. So this is actually, we're not going to cover how we do the processing, the processor. The processor is on other courses. So we have a VLSI, we have a microprocessor, those kind of things. Sometimes we do parallel processing. So that one is a computer system courses. So what we cover in this course is on how we do the processing. When we get the data, so how do we process it? Okay, combination of every courses that you learn. So you will see this. You will see this. So how every technology now becomes very, very fast. Right, and you will see later in this course, so how a convolution can be done in several ways. Okay, it's not just the one that we do, that's the only way that we do it. So actually we can optimize it, so that everything becomes faster and faster in terms of algorithm. In terms of hardware, so that will be on a different course. Okay, thank you, Karim, for that note. Okay, so all right, so we stop here. See you guys again after 10 minutes. Okay, bye everybody.